Okay, in this video we will look at the generalization of the results that we proved last time. So let me show you what we did last time. Here. So we were looking at this Feynman diagram where P is the momentum that enters into this. This is the external momentum. Okay, where P could be time-like or space-like momentum. We leave it general for now. So this is the integral that we were looking at in 4 dimensions. Okay, so you are still in 4 dimensions, but then we saw that this integral is divergent in 4 dimensions. It is ultraviolet divergent, and it diverges logarithmically. And to avoid that complication, we said, okay, we will look at this integral in 2 dimensions where this integral will converge. Okay, and that we could see by power counting. So that is why you have D2L here. Okay, the propagators are the same, but we are working in lower dimensions. Then we use Feynman parameterization. Okay, and we did some shifting of momenta. And then we looked at the external momentum. We looked at the case where external momentum is space-like. Okay, and in that case, we saw that we could rotate the contour axis, the integration contour, to the imaginary axis. Okay, and that is called Wick rotation. And then we could find the integral. There were no singularities. Okay, this is the denominator here in the integral. We found that it was positive definite, so there were no singularities on the integration contour of K2. Okay, if you are doing an integral over K2. Okay, and then we found the results for physical momenta where P square is time-like by analytic continuation. Okay, that's what we found here. And now what we want to see is that the same procedure goes through even when you are looking at Feynman diagrams which are having more than one loop. Okay, so as you know that Green's functions, the analytic structure of Green's function is going to be given by these integrals. The remaining overall factors and other things that sit in the numerator doesn't bother us, so we'll not worry about those things, and we will only worry about the Feynman integrals. So let's proceed with that. I'll draw one diagram to give you some idea of kind of denominators that we are going to get in these integrals. So, and I'm drawing it in phi cube theory. It doesn't matter because we are not looking at the vortices and other things anyway. So you could do the same thing in phi 4 theory, similar diagrams, and arrive at the same conclusion. So let's say that P1, P2 and P3 are the external momenta. Okay, so let's say P1 square is M1 square, P2 square is M2 square, P3 square is M3 square, or you could take all of them to be equal, does not matter. It doesn't change our argument. Okay, so this is a diagram of how many loops? This is a 2-loop diagram. Okay, and let's do some assignment of momenta. So I will put a loop momentum L1 to be flowing in this direction. You don't have to put it this way, you can put it differently. There are many ways in which you can assign momenta, but this is one particular choice of momentum assignment. Okay, and as you are already aware, that result does not depend on how you assign these loop momenta. Okay, so that's L1. At this vertex, P1 and L1 are entering. So what should be flowing here is L1 plus P1. Okay, then at this vertex, P2 is injected. Then what should be here is L1 plus P1 plus P2. Now here the momentum, what flows in here, is undetermined because I do not know what is coming from here. And that I don't know because this is a two loop diagram and you will need two loop momenta. They are undetermined. They have to be integrated over. So you need one more loop momentum, and let me assign L2 to be flowing in this direction. Okay. Then this one gets fixed. It is L1 plus L2 plus P1 plus P2. Okay. Okay, I want to change the direction of this one. I will put it this way. Okay. Does not matter. You can take it in also, but I'm going to take it out. Then you have this momentum L1 plus L2 plus P1 plus P2 entering here, and at this vertex P3 is taken out. So what flows in here is L1 plus L2 plus P1 plus P2 minus P3. Okay. You could have drawn this differently, and I mean not drawn, but momentum assignment could have been different. So if you took L2 to be going upwards instead of coming downwards, then this L2 would have come with a minus sign. Okay. Okay, good. So with this we see that the propagators, any of the propagators in this entire diagram, okay, has the following structure, that it is a sum of loop momenta and external momenta with some, they appear with some coefficients, okay, where for example here that coefficient is -1 and all others have appeared as +1, but as I said, if L2 was going upwards, if I had done a different assignment, L2 going upwards, then here you would have got -L2. Okay, so each of the propagator has the following structure. So it is some alpha, okay, I, Li. So you have to sum over the number of loops. So in this case, this is alpha 1 L1 plus alpha 2 L2. Okay. Maybe I should make it explicit. Later I will drop this summation, but here I will put. So I is equal to 1 to 2 for this case, plus here you have 3 external momenta. Okay, so you have beta 1 P1 plus beta 2 P2 plus beta 3 P3, where alpha I takes values 1, 0 or -1. Okay, a particular propagator may have may not have any of the external momenta flowing through it. For example, here in this one, okay, there is no P1 or P2, and in this one there is no P1 or P2. Okay. Similarly, it's possible that some line does not have some of the external momenta flowing through it. So these are the values that this alpha and beta will take. I can be a little bit more careful and put J here. Okay, so that's the structure. That's what flows in the propagators. Okay, so now what I'll do is I will look at a general L loop Green's function, and that will have, of course, an L loop Feynman diagram, and write down what the expression of that integral would be. Okay, so let's here itself. So consider a L loop Feynman diagram. Okay, so, and it has n propagator lines. So let's say it has n propagator lines, and there are E external momenta. For the above diagram, you have, for the above diagram, you have L is equal to 2, N is equal to how much? 1, 2, 3, 4, 5, 6, and E is equal to 3. Okay, so let's write down expression of a general Feynman diagram. Okay, so I will denote the Feynman diagram by F. It will depend on these external momenta, P1, P2, and so forth to PE. Then it will depend on all the masses, but let's say all the masses are equal. It doesn't change the arguments. So they are all equal to m square. Okay. Now, as you know that these Feynman integrals are Lorentz invariant objects, so they will not depend on P1, P2 separately, but only on Lorentz invariant combinations. And there are several Lorentz invariant combinations that you can make. So of course you have, given this, you can make P1 dot P1, then you can make P1 dot P2, P1 dot P3, and so forth. Okay, PE. Okay. So it will depend on these combination, these Lorentz invariant quantities. Okay, it will not depend on P1 mu separately, but on either on P1. I mean, it will depend on P1 square and P1 dot P2 and so forth, and of course similar other combinations. So in general, it will depend on Pi dot Pj, where I and j both take values from 1 to E. Okay, and also on m square. And if your momenta are on shell, then P1 square is itself m square. So that's the dependence that we have. But remember that not all these will be independent, because you have energy momentum conservation constraint. So not all these invariants are independent of each other, but I'll not worry about or writing down the arguments with only independent ones. I will just leave it like this without any harm. So it is really, Feynman diagram will have this structure. It will this dependence. Okay, I'm going to denote these L loop momenta by L1, L2, L, capital L. So, and also I want to work in n dimensions. Just like I previously worked in 2 dimensions, because the integral was divergent in 4, I want to write expressions in n dimensions. And of course, this integral will be divergent in ultraviolet, but I will pretend as if this problem doesn't bother us. And later we will see that the reason why we can ignore that problem is because we can do renormalization. But for now, we just pretend that that is a problem which is not going to disturb us. Okay. Later we'll see that we can remove these singularities, and then this analysis that I'm doing now goes through after you have done those subtraction of singularities. Okay, so I'm going to just write down expressions in general in n dimensions. Okay, so let's take a particular loop momentum Li. So d and Li, that is what will enter into the integral. and I'm going to write it as DLI0 that's a time component, and now I have spatial components, and there are n-1 spatial components Li. So if n is 4, then you have d4Li, that's dl0 d cube Li. Okay, so 4 minus 1 is 3, and in general n-1. Okay, good. So how about the first propagator? Let's call one of the propagators as propagator number 1, then another one as propagator number 2, and so forth up to propagator number what did I use for n propagators, propagator number n. So let's write propagator 1, whichever you have assigned as 1. So I'm again not keeping whatever comes in the numerators. So although I'm doing scalar theory right now, but because I'm not bothered about the numerators, this analysis will go through even for other theories like QED and other theories, okay, where you have fermions and other gauge fields. So this analysis is not restricted to only scalar theories. Okay, so propagator number, not 1, let's take it in general. Propagator number, I want to keep it 1. Propagator number 1. So you have alpha I, like I had previously written, Li. Okay, so these are all the loop momenta flowing through the propagator. Then you have beta j, pj, these are all the loop momenta that are flowing through the propagator. But then I should put a label 1 to remind me that this is for first propagator, square it minus m square, and this is our I epsilon coming from I epsilon prescription. Okay, and I have dropped the summation. So summation convention is now implied. So alpha I, Li is basically alpha I, Li, where I runs from 1 to the number of loop momenta, which is L. And similarly, beta j, pj, beta 1j, pj is j equal to 1 to the total number of external momenta, right? Because we are adding this sum here contains e number of terms. So beta j 1 pj. Okay, that's one of the propagators. And similarly, you will write for other propagators. So propagator number m will have same thing, but only this index 1 will get replaced by m. So alpha I m Li plus beta j m pj square minus m square plus I epsilon. Okay, good. So now let me write down the expression, which will be just writing dnli, okay, so dnl1, dnl2, so forth, and each time you divide by 2 pi to the n. So I will always divide by 2 pi to the n. In 4 dimension, that division is 1 over 2 pi to the 4. And here it will be 1 over 2 pi to the n. Okay. So we have to just do that integral. Does it help in writing? Okay, maybe I'll write it, this entire integral again. It's a little wastage of time, but I think it will make reading things easier. So f pi dot pj m square is d NL1 over 2 pi to the n, and these integral limits run from minus infinity to plus infinity, and then you have dnl total number L, okay, that's the loop number of loops, 2 pi to the n, okay, and what do you integrate over is these propagators. One over alpha I1 Li plus beta J1 Pj square minus m square plus I epsilon This is the integral that we have. Total number of propagators is n, so that's why this is index n, okay, plus beta j n pj whole square minus m square plus I epsilon. So that's the integral which we want to study. Okay, and these alphas and betas take values 0, plus 1 and minus 1. Okay. Now we will use our old technique of using Feynman parameters to combine these denominators. Okay, so let me go to the next page and I'll come back to this one again. Here, Feynman parameters. So I'll need to use a formula that is generalization of the formula that I have shown you earlier. Let me go back and see where it is. Yeah, here. So here we had 1 over a1, 1 over a2 as integral over dx with these factors. Okay, where 2 is this 2 is coming because you have two functions, a1 and a2. Okay, so I'm going to write a generalization of this formula when you have several such functions a1, a2 and an, and the result is the following. So this is just multiplication. 1 over a1 times 1 over a2, so on and so forth, times 1 over an. This is integral 0 to 1. Okay. Integral 0 to 1 dx1, so that's x1 is one of the Feynman parameters, and actually there are n of them. Dx n, this n is this n. This is not the number of dimensions. Okay, this is I'm writing for if you have n factors. 0 to n 1. And then you have a delta function that constrains these x1, x2 values. So it says x1 plus x2 plus so and so forth plus xn minus 1. Meaning this delta function hits only when the sum of all these Feynman parameters is equal to 1. Okay, not otherwise. And then the integrand is this. So all these denominators a1, a2 and a3 up to an, they nicely combine. And they give you x1 a1 plus x2 a2 plus xn a n, and the power is n. Okay, and here we have a prefactor which is gamma n. So gamma n is our familiar gamma function. Okay, and you know that gamma n is equal to n minus 1 factorial if n is integer, but gamma n is also defined for non-integral values. Okay, you have gamma n defined for complex values as well. So this is the Feynman parameterization, and this is what I'm going to use in manipulating the function here, the integral here. Okay, so using this I can now write down this expression as gamma n. So I'm including this. First I'm putting the Feynman parameter integrals dx1 dxn okay, so that's the delta function. Then you have integrals over loop momenta. Okay, and these run from minus infinity to plus infinity. And then you have all these denominators have been combined. So you have x1 alpha I 1 Li plus beta 1 j plus pj, okay, that whole squared minus m square plus epsilon. So this is the contribution from the first propagator, and this gets multiplied with x1. Okay, and then you have the remaining ones, and the last one gets multiplied with xn, because we have n such denominators, capital N denominators, because we have capital N propagators. Okay, so for each Feynman propagator we have introduced one Feynman parameter. Okay, that's what we have done. So alpha I n Li plus beta j n pj squared, this entire thing squared, minus m square plus epsilon. Okay, and then this thing raised to the power n, because we have n number of propagators. Okay, so this is what we have to now analyze. So let me first look at this term. We have x1 multiplying minus m square. Then you have, next term will have x2 multiplying, okay, x1 multiplying minus m square plus epsilon. Then you have x2 multiplying minus m square plus epsilon. And the last one is xn multiplying minus m square plus epsilon. So that is easy to deal with. So x, so what you get is minus m square plus I epsilon times x1 plus x2, so on and so forth, plus xn. Okay, but then the delta function here that you have says that the sum has to be equal to 1. If it is not equal to 1, then the integral is 0, right? It doesn't hit. So that condition has to be satisfied. So I can already use that condition here and put the sum to be 1. Okay, or let me make it more explicit. This is equal to minus m square plus I epsilon times, okay, Yeah. See, this is in the denominator and it doesn't come like a product like this. But it is because of this delta function that I should put this equal to 1. So you cannot use it directly and put it there, but I hope you understand this argument. Okay, so then I will just replace, as far as this minus m square plus I epsilon from each term is concerned, I will just have this thing will just sit outside of all these alpha Li plus beta j Lj terms. Okay. Okay, so that one part is done. And now I'll write this again, but this time I will also write explicitly the integral over time components of the loop momenta. Okay, I will make that explicit. So I'm not doing much, I'm just carefully writing everything again. So this Feynman integral is now gamma n and then dl1 zeroth component of it, dl1 the remaining n minus 1 components, I'll just write here, and then so these limits are for all the variables, okay, not just for the zeroth component. So dl0l, dll n minus 1, okay. This small n is for the dimensions in which we are working, times okay, let's write it carefully. Okay. So, or maybe can do a little better. Okay, let's see. So we have, first I will write down the time components, or even better in just a second. Yeah, doesn't matter how I write it. So you have x1 alpha I1 Li0 beta j1 pj0. So that's the time component, and that has to be squared. Okay, so this is this one. So I have just written the time component part of this, right? So if you take this entire thing as q square, then I have written q0 square, and I should now write down minus q vector square. Okay, that's what I'm doing. So minus, this is in the denominator, okay, so this minus this square is what makes up the first term in this denominator. Okay, and minus m square plus I epsilon, I'm going to write at the end. Then you have okay, let's keep it a little bit space. xn alpha I n li0, correct, plus beta nj pj0, that's squared. Okay, and I should have similarly here the square of the space component, which is alpha I n li plus beta j n pj squared. Okay, and then you have minus m square plus I epsilon. And this entire thing should be raised to the power n. Okay, so that's what we have for this integral. And I should see whether I can repeat the same line of reasoning which I had earlier for the case of one loop. Okay, I will now just copy this entire expression. Let's see if I can. Toolbar, yes. There's another way. Take this and duplicate. Okay, good. So that's the Feynman integral which I want to evaluate and look at its analytic structure. I'm not going to evaluate it actually. So now let's take this integral and modify it slightly. So I will define a new function, new integral, which I call f tilde. Okay, so this is different from f. Let's see, yeah, f tilde, where the difference is the following. So this f tilde I define by replacing the following. I make the following replacements in f. So what do? I say L10, okay, this I define as e to the I theta L1 n. Okay. This n is referring to the number of dimensions. Okay, this is, let's go back. Here you remember I had e to the, k to the 0 is I times k2. And this 2 is for the number of dimensions, right? k0, k1, then k0 I label as k2 times this vector. So I go to a two-dimensional space, k0 and k. Okay. Similarly, because I'm in n dimensions, so I have these space components as k1, k2 up to kn minus 1. The 0th component I am redefining using kn. Okay, so that is the notation. Good, and not only for loop momentum, I'll do the same thing for so this is for all the loop momenta, so I'll put an index I, and the same thing I will do for all the external momenta. So if I take momentum pi 0, 0th component of pi, then I define pin to be by this relation. Okay, so if I do that, and also before that I restrict theta between 0 and pi by 2. Okay, I think now I've said everything that I should. Good. So theta from 0 to pi by 2. So here this is fine, this dn this DL10 will become DL1. Yeah, there is no gain in copying this. I have to unfortunately rewrite it. Or maybe I will not. Okay, maybe I'll not. I'm a little tired of writing this over and over again. So DL0 I should replace by e to the I theta Lin. Okay, and similarly here. And then what are the other places? Here Li0, here Li0, they get replaced. And in this in this Pj zeros. Okay, so if you look at the first line here, this entire thing gets modified, right? Because it picks up a factor of e to the 2I theta, right? Because each term here is multiplied by e to the I theta square, which is e to the I 2 theta. So everyone is multiplied by e to the I 2 theta. So that's the factor it picks up. And nothing happens to these, and there is some factor of e to the I theta coming from each of these here. Okay, so let's look at the denominator. Only the denominator. So denominator. What's the structure? Structure is I will drop these labels. I will this one here and n here, I will just suppress it because it will be easier to write that way. So the denominator is summation over all those indices that I am suppressing. I am not showing here, and it is x alpha I L I0 plus beta j pj0 squared minus x alpha I Li plus beta j pj squared, and then also have minus m square plus I epsilon. Correct? That's the denominator. And you understand the sum is over these suppressed indices. Good, and this is the denominator of f, and denominator of f tilde is what? Is summation x alpha I. Okay, now this becomes alpha I Li n plus beta j pj n squared minus times cos 2 theta plus I sin 2 theta. Okay, this is the factor e to the I 2 theta. And then you have minus okay, that's what we have. Good. So now let's take theta to be pi by 2 and see what happens. So if theta is pi by 2, this is e to the I pi, okay, and this is so e to the I pi, and e to the I pi is minus 1. Okay. Now, when this factor becomes minus 1, okay, here it is anyway square of all real numbers. See, Lin, they are all real. So, Lin, they are real. Okay. So, if Lin are real, the square is going to be a positive number. This provides you with a minus 1. Okay. So, this is minus of some positive number. This is similarly here, minus of some positive number, then you have minus m square. So that's again a negative number. So this denominator, other than this I epsilon, is a positive, it's a negative definite number. Okay, or if you take out minus I overall, it's a positive definite quantity. It has a definite sign, it doesn't change somewhere. And because it's negative definite, it never goes to 0. Right? Here, I should put n, that is the denominator. So this denominator never vanishes. Okay, so it is well defined for theta equal to pi by 2. Okay, this is what is Wick rotation. So let me write it down. So we have the denominator is a negative definite quantity, is minus 1 power n times a positive definite, okay, because I have pulled out minus 1 power n, positive definite. Okay, and then I don't need I epsilon, right? Because if this denominator never becomes 0, then you don't have to have an I epsilon. Okay, it doesn't become 0 when on the LIN axis. So I will drop that I epsilon. So this is well defined because there are no poles on LN integration contour. Okay, and I have also included this minus m square in the argument, right? Because that just adds up. So this integral now can only be a function of okay, so let me show. Note that this integral can only be a function of so I earlier told you that it is a function of pi dot pj. I am taking theta equal to pi by 2 now and arguing about f tilde for theta equal to pi by 2. So this is I pi n dot I pj n. This I is complex I, okay, minus pi dot pj. Okay, pi and pj are the external momenta. Ith external momenta, jth external momenta. So that's what pi dot pj is. And I square is minus 1. So minus summation over whatever. Let me write explicitly. So pi n pj n minus pi 1 pj 1 pi 2 pj 2 up to pi n minus 1 pj n minus 1. Right? Sorry, I made a mistake. I should have a plus because I have pulled out a minus sign. Okay, which is what you write as pi dot pj. So you see that this dot product now, this that enters into the function f tilde doesn't have, the dot products are not Minkowskian, right? The signature is now not minus 1 plus 1 plus 1 so forth, or plus minus minus. So here the signature is Euclidean. Right, so you don't have pi 0, pj 0 minus something. All the terms are added together. So this is what you have in Euclidean space. So the signature is plus 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 up to n times. Okay, so this is what is usually defined as the Euclidean Green's function. So that is f tilde with this pi dot pj m square, and if you put theta equal to pi by 2, then this is what is called as Euclidean Feynman integral pi dot pj. You have to evaluate it with this signature, so I will make it explicit by putting Euclidean here, and then you have m square. And because these Feynman integrals enter the green functions, correspondingly the green function will be given by this. So this is the expression for the Green's function. This is called Euclidean Green's function. Okay, good, but we still have to do a little bit more work to say something about our original function. So now let's look at what happens when theta is between 0 and pi by 2. Okay, when theta is between 0 and pi by 2, here, so when theta is between 0 and pi by 2, okay, I want to look at the imaginary part of the denominator. And from where do I get those imaginary parts? So these are all real objects. Okay, m square is real. There is one part coming from I epsilon and another coming from this I sine 2 theta term. Okay, that is what gives you the imaginary part. Now sine 2 theta will be positive when theta is from ranges in the region 0 to pi by 2. So that's positive. Okay, this overall coefficient which multiplies this is also positive. Okay, so the imaginary part, and here also epsilon is positive. Okay, so here the imaginary part is positive, definite. Okay, so which means that there are no singularities in the integrand in this region. Okay, because that is positive, definite. When this, the denominator, the remaining part of the positive of the denominator is positive, definite. Okay, so it means that there are no singularities in the integrand in this region. Okay, you are integrating over all the real values, right? The integral has all this here. So when you are integrating this denominator, you are integrating over Lin, which takes real values. Okay, so because there is an imaginary component which is negative, which is positive, definite, you are the denominator, it never becomes 0 on the axis of on the contour, on the integration contour, right? So it never becomes 0. So there are no singularities, and now your integrand is an analytic function. There are no singularities. And when you integrate such a function, such an integrand, what you get is again an analytic function. Okay, so what does that mean? How does that help? Yeah, before that, I will tell you how it helps, but before that, pay attention to the fact, to the I epsilon here. Okay? If it so happened that the imaginary part coming from here, okay, coming from this term, or precisely from this multiplying this, came out to be negative, okay, instead of positive as we have got, then it could cancel this I epsilon term, right? Because you get minus I times some quantity, and for some values of these other variables, that equals whatever I epsilon you have chosen. So there will be a 0, there will be a 0 sitting, there will be a pole that you will have in the function. So it will not be an analytic function, and integrating it will not give you another analytic function. So here we have seen that the way we are rotating the contour, okay, in this manner from 0 to pi by 2, we do not have any singularities that appear. So what is the upshot? The upshot is that our G tilde or F tilde is same as what was here, m square, and then we had a theta, is same as G tilde with, sorry, not 0. If you put 0, then it is same as G pi pj m square. Okay, so that's the same Green's function for this value of theta, and this is what we want to understand, right? Whether this is well-defined object or not. So as far as G tilde is concerned, G tilde is same as G when theta equal to 0. Then G tilde is an analytic function for in this range. Okay, so G tilde is analytic in this entire range. And also G tilde is well defined when we have taken theta equal to pi by 2. Okay, that is the Wick rotated Green's function. So that Wick rotated Green's function exists because we saw that there are no poles on the contour. Okay, and then G tilde, then it says that what it means is that the G tilde provides the analytic continuation of the Wick rotated Green's function, and then we can continue this G tilde for theta equal to pi by 2, which is well defined, to G tilde here. Okay, because this is an analytic function, I can get a analytic continuation for that. Okay, so this with this we have argued that these objects are well defined. We can compute them and also find their analytic structure by using this continuation from this Wick rotated Green's function to the Green's function with physical momenta. Right here the momenta are not physical, okay, because we have taken space-like momenta, and which we saw here. Where was that? Yeah, here you see that pi dot pj, which is what enters in the Green's function, this is positive, okay, because this is Euclidean and there is a minus sign. So you see all these dot products are negative, all the momenta pi square, they all become negative. So that's why I'm saying that they are space-like. So you can go from this Green's function defined for space-like momenta and all space-like dot products to Green's function which is defined for physical momenta, in which you are interested in when you are looking at scattering processes, right? Because when you look at scattering processes, the external momenta are on shell and they are physical momenta. So this proves that we can finally do analytic continuation and everything is well defined. Okay, we will continue further in the next video.